Okay, now let's look at this question. The uniform 22.68 kg slender rod is subjected to a couple moment of 135.6 Newton meter. The rod is at rest when theta equals to 0. So from here we know that this thing is gonna move in this direction. Okay, so this is the initial position at this point, a vertical, and because of the couple moment applied to the rod, it will start to rotate in counterclockwise direction going up, and this will be the second or the final position of the rod. So you can see here that we have a weight at point G. This is point G, and obviously point G is now moving up here. So this is point G number 1, this is point G number 2. So you will see that there is a change of height of point G, and therefore we have delta Y here, and there is definitely a work done by the weight. So we can first start by calculating the work done by the weight. That is UW equals to minus delta Y times W times the weight. So if you notice, because of this minus sign here, whenever the rigid body is traveling down, it will have positive work done by the weight. But whenever the rigid body is traveling up, the work done by the weight is going to be negative. So here we have delta Y is definitely the length of the rod divided by 2, okay, which is 1.524 divided by 2, multiply with the mass M and the gravitational acceleration G. This indicates the weight. So you have minus 169.5 joule for the work done by the weight. Next is we also have the couple moment applied to the rod. So definitely there will be work done by the moment, because there is angular displacement involved. You notice here from 0 degrees to 90 degrees. So the angular displacement, the change or delta theta here is 90 degrees, which in fact is equivalent to pi over 2 radian. So we have here the work done by the couple moment is the moment itself multiplied with the angular displacement. So you have 135.6 multiplied with pi over 2. You have 213 joule. That is the work done by the moment. Now, we would like to calculate the angular velocity of this rod when it reach the horizontal position, that is theta equals to 90 degrees, and it says the rod is at rest initially. So we know that initial kinetic energy T1 is equal to 0. Next, we need to know the final kinetic energy, and in this case the rod is undergoing rotation about a fixed axis at point O. So the kinetic energy for rotation, we have two different equations to calculate. So now I'm going to demonstrate how you can use this first equation, that is T2 equals to 1 over 2 mv square plus 1 over 2 ig omega square. But the problem here is that we don't know what is Vg. Okay, what is Vg in this case? So you still remember that in kinematics we have V equals to omega times R, right? So we can use that when the rod reach the position number 2, this is position number 2, then Vg is pointing up. All right, so if you can imagine, Vg is always pointing, this is the first position, so Vg in this case here will be pointing this way. This is Vg. All right, when it reach this position, then Vg is pointing this way. This is Vg, right? So you can see that Vg is basically following a circular path. All right, so from here at position number 2, Vg is equal to omega times r. R here is definitely half of the length of the rod, which is 1.524 divided by 2, and omega here is omega 2, so you have Vg is 0.762 omega 2. Now let me erase this. Okay, and now we have the first term. Now to calculate the second term, which is this one, the second term, we need to know what is Ig here. So this is a slender rod, and you know that Ig from the table is 1 over 12 ml square. So you can substitute all the values in this equation to get Ig is equal to 4.39 kg meter square. Then we can substitute all the values in the equation of the final kinetic energy, and we will get T2 is equal to 8.78 omega 2 square. This is the parameter that we would like to calculate. This is the angular velocity at theta equals to 90 degrees, or at position number 2. Right, so we will be using the principle of work and energy that we have discussed previously. This is the principle of work and energy. Okay, so you will substitute all the values. T1 is equal to 0 because it starts from rest. The work done, there are two work done here, work done by the weight and also work done by the moment. So you're gonna have to put all these two to sum it, to get a sum of it, and equal to T2, which is 8.78 omega 2 square. And in the end, finally, we will get the value of omega 2, which is equal to 2.23 rad per second. And as I've mentioned earlier, you have another alternative to calculate the final kinetic energy. That is by using T2 is equal to 1 over 2 IO omega 2 square. Now you are calculating the mass moment of inertia about the center of rotation O, about the center of rotation. Okay, now to get IO, you will have to use the parallel axis theorem. Okay, remember that this is the parallel axis theorem, and parallel axis theorem states that IO is equal to Ig plus md square. So Ig in this case is the one that we have calculated before. M is the mass and d is the distance from the center of gravity. This is the center of gravity G to the center of rotation. So basically this is the parameter d. So parameter d is indeed equal to half of the length of the rod also, so 1.524 divided by 2. So you will get IO equals to 17.56 kg meter square, and therefore we get the same value of T2, that is 8.78 omega 2 square, And again, we use the principle of work and energy, T1 plus the total work done to move from point 1 to point 2 is equal to the final kinetic energy T2, and in the end we will get the same answer like we have before, 2.23 rad per second.